structure shows valence electrons. What else? What we got? Okay, it shows the bonds between atoms. It shows actually how the atoms are arranged in a molecular compound. Anything else we should add to this? Actually, that was pretty good. So it shows how the atoms are actually arranged. It shows the physical structure of a compound. And these are all compounds that are held together covalently. So this is used for covalent compounds. Used for covalently, we'll just say covalently bonded stuff. I say covalently bonded stuff because it can also be used for polyatomic ions. We haven't talked a whole lot about those yet. We've sort of hinted at them, but we'll be talking more about them soon. Okay, so that's what a Lewis structure is. Okay, so we're going to start off. This is ammonia, NH3. So it's 1 nitrogen, 3 hydrogens. And if we're doing it the fumbly, old, silly way, this one actually isn't too bad. So we would start off drawing Lewis dot diagrams for each of them. How many, you need your periodic table out. How many valence electrons does nitrogen have? Okay, nitrogen has 5 valence electrons. So we go whoop, 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 whoop. Looks something like that. So there's nitrogen's electron dot diagram. How many valence electrons does hydrogen have? Just show fingers. 1. Hydrogen has 1 valence electron, and so we can show our little hydrogens here. So I've got 3 hydrogens, each with 1 valence electron. This is pretty easy because they hook up pretty easily. No big crazy challenge to this. We can kind of figure out where all these are going to go. And they plug in kind of like puzzle pieces. Okay, so because, of course, each of the hydrogens just had 1 electron, they just kind of plugged in pretty easily. Once we've got those shared pairs that are bonding it together, then we can just replace each pair with a line. So we've replaced any place where it was sharing 2 electrons like this with a line like that. The one thing that we cannot get rid of, that we have to keep and we have to show, is these unshared. This is an unshared pair. So it is a pair of electrons, and they're not being shared between 2 atoms. They belong to nitrogen alone. Important things here. So here are the big important things when you look at a finished Lewis structure. You can't ever have 1 electron by itself. Ever. You can have unshared pairs, but they're kind of like, your codependent friend who can't go to the bathroom by themselves. No electron can ever just be alone in these things. They have to be paired up. And if we think about 2 electrons per orbital, that's kind of what we're looking at. We're looking at full orbitals. They're not stable, really, till they get 2 electrons in an orbital, so they have to always be in pairs. These represent pairs, each of those lines, and then we have unshared pairs. The other thing when we finish a Lewis structure is to check to make sure everybody's happy from an octet perspective. So everything has either 8 electrons surrounding it, or it's got whatever it is that makes it happy, because we have some exceptions to the octet rule, if you remember. So let's look at nitrogen first. So for nitrogen, we have 2, 4, 6, 8. Nitrogen's satisfied from an octet perspective. Hydrogen. How many electrons does hydrogen need to feel satisfied? 2. So this hydrogen has 2, this hydrogen has 2, this hydrogen has 2. Satisfied. And yes, we are double counting those lines. Those lines count as 2 for each hydrogen. They also count as 2 for nitrogen. That's the nature of sharing. In reality, nitrogen owns one of the electrons, hydrogen owns one of the electrons, but they feel like they've got access to 2. And that's the nature of chemical bonding. That one's easy to do the old-fashioned way. We didn't do any math ahead of time. We didn't do a whole lot of counting. We just kind of drew Lewis diagrams and plugged stuff in, and it all worked out. It doesn't always. So let's do one that's a real nightmare. And then you'll kind of see, then I'll give you the gooch math, and you'll see why it's an absolute sanity saver. So we have CO2. Okay, 1 carbon, 2 oxygens. Seems like it should be simple enough. What does the electron dot diagram look like for carbon? Well, I should say, how many valence electrons does carbon have? Periodic tables. How many valence electrons vote with? And so carbon's electron, I always think carbon looks like some sort of tribal tattoo. I don't know. Or just like a Celtic ruin of some sort. It's not. But you can think about how cool carbon is. Oxygen, how many valence electrons? 6. So oxygen's electron dot diagram looks like that. And we have 2 of them. Okay. Well, this seems easy enough. We can just sort of, well, wait, I can't fit this oxygen onto that carbon. The electrons are all on the wrong side. Anybody have any objections for me? Well, the dots aren't really electrons. So, just because I drew the dot on this side of the oxygen doesn't mean it has to stay there. So, can we do that? And plug, whoops, and then take this and move it over here? Sure we can. Am I done? What's wrong? I have not unshared pairs. I have singletons. I have a bunch of electrons that are all by themselves, and that cannot be. So what are they going to do? They're not stable in this configuration. What are they going to do? Carbon and oxygen are going to end up sharing them. So what we very often show, and the way that I learned to do these, and I find it confusing and horrifying, and I could never, well, am I allowed to move this here? Am I allowed to do that? We just move them. Where do they come from? Where do they go to? Nobody cares. No, people care. Now I have, what is this representing? What kind of bond? Double bond, sharing 2 pairs. Guess what's going to happen to those other electrons over here? Same thing. We're going to create a double bond. And now once we've got the the shared electrons shown, we can go ahead and replace those with lines. Now what I can't get rid of are those unshared pairs on oxygen. So this has got 2 double bonds. This seems horrifying. Here's the thing that always gave me fits and panic attacks. How do I move the electrons? Where can I move the electrons? Oh my gosh, what forms a double bond? Just keep moving stuff around. Ah! There's an easier way, especially if you like to have numbers to back up what you're looking at. So what I'm going to share with you is called the Gooch method. It is named for a chemistry teacher named Mr. Gooch, who for years ran a website, an awesome chemistry website, and I completely stole his method, and I stole his handout, and we're going to walk through it. So let me hand it to you. Okay, so we're going to use the Gooch method, and we already have arrived at an answer here. Okay, we know that that's the right answer. We've got it set aside. But what we want to do is see how we back that answer up numerically. So with the Gooch method, the very first thing you do, step 1, I should do that in a different color, is count the valence electrons that each atom is bringing to the table. So how many valence electrons? So carbon has 4, oxygen has 6. There are 2 oxygens. So we have 4 plus 12. We have 16 valence electrons. That's step 1. Val E. Okay. Step 2 is to figure out how many octet electrons everything would be happy with. So I'm going to shrink this step just a little bit. Step 2. Octet electrons. Well, carbon wants 8, oxygen wants 8, and there are 2 oxygens. So we have a total here of 24 octet electrons. If everybody had all the electrons they wanted, there would be 24 of them. The third step is to figure out how many they're going to have to share. So number 3 is octet electrons minus the available valence electrons. So here we have 24 minus 16. 8 valence electrons will be shared. Eight valence electrons will be shared. And step 4 is, how many bonds is that? Well, that's easy. A bond is comprised of how many electrons? 2. So if we take the shared electrons and divide by 2, that equals the number of bonds. In this case, we have 8 valence electrons divided by 2. We have 4 bonds that we're expecting. The last step, step 5, is finding out how many are unshared pairs. So to do that, we look at how many electrons everything came in with. We look at the valence electrons, and we subtract the number of shared electrons. So in this case, we came in with 16. We're sharing 8. That means there will be 8 unshared electrons. Now, if we were doing this cold, we didn't have the answer sitting here staring at us. What this would lead us to do, let's see. Well, what goes in the middle? Carbon always goes in the middle if there's carbon. In other cases, if you have one of one kind of atom and multiples of everything else, the singleton goes in the middle. Okay? So in this case, we would put carbon in the middle. We know that there have to be, so we've got oxygen, and there are 4 bonds here. The only way to do that is to put in 2 double bonds. We know that we have 8 unshared electrons. We know they only travel in pairs. 1, 2, 3, 4, 5, 6, 7, 8. Hey, guess what? Same answer that we arrived at the other way. As we're doing Lewis structures, I'm going to expect you to show your gooch math. Pain, but it's okay. I'm going to give you some practice on doing these. We're going to kind of workshop these today. Tomorrow, let's see. I know what we got to talk about. Ions. So, do you remember what a polyatomic ion is? We talked about these briefly when we talked about ions, gaining and losing charge. You know, an ion is a charged atom. What does poly mean? More than one. Yeah, many, more than one. Polyatomic ions are ions that are made of more than one atom. So they're groups of atoms that are covalently bound, they're sharing electrons, but then as a group, they've gained or lost electrons. So we'll look at a really simple one first. This is the ammonium ion, NH4 1+. So 1 nitrogen, 4 hydrogens, and it's lost 1 electron. We know it's lost 1 electron because it is 1+. It's got 1 more proton overall than it does electrons. So if we remember that nitrogen looked like this, and hydrogen just has 1 electron, it was really easy to fit 3 hydrogens around a nitrogen, but in order to add 1 more hydrogen, we would have to do something. We'd have to get rid of 1 of those electrons. Okay, easy enough. This is the simplest of the polyatomic ions to do a Lewis structure for. You can do this the old-fashioned way with no math, and it's not even painful. But if we do it with the math, then when you do the more complicated ones, those aren't painful either. So let's do this one with the gooch math. We'll start off like that. First step, what do we do? Step 1. Count your valence electrons. Okay, nitrogen has how many coming in? 5. So nitrogen has 5. How many does hydrogen have coming in? 1. So that gives us, and this is times 4, that gives us a total of 9, but there's something that we're forgetting. It lost 1. So minus 1 electron, this actually has 8 valence electrons. I'm going to have to really shrink this. Okay. Step 2, count the octet electrons. How many does nitrogen want? How many does nitrogen want? Octet electrons. 8. Overall. It wants to feel like it's got a set of 8. How many does hydrogen want? 2. And there are 4 hydrogen. So our octet number is 16. Okay, so bracket charge, did the gooch math, you've got the gooch math handout, and I'm going to give you some to practice on and float around.